Hello everyone, this is Professor Roman, and this is the third course in my series, Abstract Algebra Comprehensive Introduction. If you've been following my YouTube lectures in mathematics, then you may recall that I have done several lectures. Here's a list. The first lecture series I did was a very short course on category theory with six lectures. Subsequent to that, I did a course entitled Transition to Advanced Mathematics. That is a 30-lecture course. It is the lectures basically that I give at the University of California, Irvine when I teach the course there. Then comes the Abstract Algebra series. The first volume was Linear Algebra. That had 50 lectures. The second volume was Group Theory with 37 lectures. And we come now to the Ring Theory course, which will be, by the way, shorter than the other two algebra courses. Originally, I had intended to do ring and field theory together as a single course, but recently I changed my mind and decided to split the two courses. Each of my courses is accompanied by a textbook. It's really better to say it the other way around. I wrote the textbook first, and then I used that book for the lectures. So the lectures primarily consist of a page-by-page look at the textbook. But the books are available on my website, www.sroman.com. As to this volume, the prerequisites are some understanding of linear algebra and some understanding of group theory. Mostly elementary things from the first parts of those two courses. Since this is the third volume in the Abstract Algebra series, I feel that I can rely a little bit more on your what is generally known as mathematical maturity, and so I can be a little less generous with some details, leaving them for you to fill in. It's important that you begin doing that, and this seems like the right time. If you have followed the first two volumes of this series, Linear Algebra and Group Theory, now then you're about to embark on a study of your third major algebraic structure, namely rings. In the introduction to the group theory course, I discussed the common themes that run through much of abstract algebra. And I did that in the context of what I called a widget, which is just an arbitrary algebraic structure. It could be a vector space, a group, a ring, a field, a lattice, whatever. Some of those common themes I discussed in the introduction to the group theory course are, of course, the definition and simple consequences, subwidgets, morphisms of widgets, and quotient widgets. So we have already discussed in those other courses subspaces, morphisms of vector spaces, which are called linear transformations, and quotient spaces. In the group theory course, we discussed subgroups and normal subgroups, morphisms of groups, which are called homomorphisms, and quotient groups or factor groups. I can add a couple more items now to this list that wouldn't have made any sense earlier since you hadn't encountered them yet, and that is the isomorphism theorems, which we studied in the linear algebra course as well as the group theory course, and the correspondence theorem. which we also covered in both those two previous courses. As we begin this course, we will go through all of these common themes. And while much of this will seem quite familiar, there will be specifics, of course, that apply only to rings. I suppose perhaps the biggest difference in the three subjects at the elementary first step level comes with regard to the substructures that are required to form quotient structures. For a vector space, you can factor out by any subspace and get a quotient space. For groups, however, as you know, you can only factor out by normal subgroups to get a quotient group. The subgroup must be normal. For rings, it's a tiny bit more complicated. We will require all our rings to have a multiplicative identity, and therefore all our subrings must have that identity. But it turns out that the only subrings then you can factor by are the trivial subring and the entire ring. So we need a new structure. It's not enough to impose an additional property as we did in the group case, that is normality. Here we're going to have a slightly different structure called an ideal. And those are the structures that we can use to form quotient rings. So all that will become clearer as we get to the material. Once the customary first steps that we've just talked about are dispatched, whether you're studying linear algebra, group theory, or ring theory, then the subjects take a decidedly different direction. So specifically, when we studied vector spaces, after getting through the fundamental details here, the beginning details, we spent quite a bit of time studying similarity of matrices because of the important connection with representations of linear transformations. And that culminated in the construction of a complete invariant for similarity. It was quite a struggle to get to that point, and it wasn't very pleasing outcome, really. We did find a complete invariant, but they're not very much fun to work with. The multiset of elementary divisors or the multiset of invariant factors of a matrix. On the other hand, when we studied group theory, after the initial steps, we spent our time analyzing the structure of finite groups using group actions. And then we established the CELO theorems. And that enabled us to determine the structure of all groups of order 15 or less. So we studied the structure of finite groups, at least at the very beginning stages. We discussed how complicated a problem that is or was to determine the structure of finite groups. And so you may recall that discussion. There's still much of it still needs to be resolved in some sense. As to ring theory, it seems to me, arguably, that the study of the structure of rings is much less accessible at the introductory level, at our level, than that of the structure of finite groups, again, at the beginning level. So after we get through the first steps in ring theory, ring homomorphisms, quotient rings, and so on, we will turn, as is customary in elementary ring theory courses, to the study of a variety of special types of rings, specifically integral domains, principal ideal domains, unique factorization domains, and Euclidean domains. And also, as is customary in elementary ring theory courses, we'll examine the relationship between these various types of rings. Then we'll spend time discussing one of the most important rings of all, namely the ring of polynomials over a field. And this material is going to be critical to us when we study field theory, in particular Galois theory. That will be in the next volume. And we'll conclude this course with a discussion of certain finite conditions on rings, namely the ascending chain condition and the descending chain condition on ideals. As you study the various branches of abstract algebra, you may find, and I think many do find, that you like one branch of algebra, maybe group theory, more than another branch, maybe ring theory. But it is important to keep in mind that each of the branches of algebra depends in no trivial way on the others. So, despite your feelings for one subject or another, it is important to at least gain some measure of fluency in each of the branches in order to be successful in any one branch. Okay? I too have my likes and dislikes, but I'm not sure that it would be the best thing to share them with you right now. So. Let's take a look here at the table of contents for this course very briefly. It will bear out some of the things I've said. We're going to start by looking at the definition of a ring, some simple properties of rings, and subrings. Then we'll look at ideals and quotient rings. Following that, we'll take a look at ring homomorphisms. Then we'll begin our look at special types of rings, integral domains, unique factorization domains, and Euclidean domains. Then we will turn to a study of polynomials over a field primarily, and finally the chain conditions, ascending chain condition and descending chain condition. And as you can see here, the book is considerably shorter than the linear algebra and group theory books, so this is a shorter course.